We are talking about a substance. We're going to focus on matter, and there's a few things that we're going to talk about in matter. So really, we want to talk about a substance. And so how do we classify? How do we classify or describe a substance?
Isn't it like it's an
Well,
element?
hold on. So can someone give me an example of just a substance, any substance?
Sodium.
A galvanized pipe.
Okay, we'll go with sodium. There's a pile of sodium. So this is why I might be a little bit challenging. There's a pile of sodium. How would you describe it?
Coarse.
White
Okay.
Salty.
Well, so sodium itself isn't actually salty.
It looks white.
Okay, it might be white, salty. Somebody said coarse. What else do we have?
Powdery substance.
Maybe powdery. What did you say, Miliana?
Crystals, they crystallize.
Okay, it might be crystals. So all of these things that we're talking about, these are all properties. These are the description or characteristics of a substance. So now I'm going to tell you a substance. I'm going to tell you, at a, let's say at a crime scene, they find a pile of finely divided white powder. Okay, finely divided white powder. What might this white powder be, do you think?
Coke.
Oh my goodness. You immediately go that route. Okay. Tell you a little bit more about it. It is highly addictive. It's very, very, lots of people are addicted to it. And you take too much of it. If it's pure,
Sugar?
hold on. It's pure and you take, a small, I'm trying to find, if it's pure and, the end of this charger here, that silver spot right there. So if you completely covered that in this pure substance and you take it into your body somehow, it will kill you. What do you think it might be? We know Kaylee thinks it's Coke.
Well, that's very.
Andres thinks it's Coca, which I'm assuming is Coke.
Fentanyl.
I'm gonna go with it's a very generalized characteristic, so you really can't say what it is.
Yeah.
Cyanide?
Okay. Cyanide? Probably not cyanide.
No.
I
Fentanyl.
heard someone say fentanyl.
Sodium chloride?
It could be sodium chloride, although sodium chloride is not terribly addictive. What if I tell you this thing is, 100 times more lethal than cocaine?
Angel says it's nicotine.
Okay.
Heroin?
More
The
lethal
hair-
than Coke.
Yeah, 100 times more lethal than cocaine.
Meth.
Caffeine.
I'm still gonna go with sugar.
Wait. What'd you say, Malik? We didn't hear you. What'd you say?
Caffeine.
That's correct.
Oh.
It's caffeine. Okay. Caffeine is more addictive than cocaine and heroin, and it is actually quite a bit more deadly. And that's because the amount that you would of pure cocaine that you could ingest, if it were the same as Coke, it would be, enough to kill a person. And so, even though we were talking about, white powder, very fine, we could talk about things like, does it feel really heavy? We can talk about its density. These are all properties, ways we can describe them. Now, there are two ways or two types of properties. There are physical properties. And chemical properties. What do you think are examples of physical properties?
What you've described just recently, like white powder, stuff like that. Anything that like describes the way it looks or smells or tastes.
Okay, looks, smells, tastes. It's more than just that, though. Okay, a physical property is something that we can determine without altering the composition. Okay. So we can determine this without altering its composition. So if I say something as white, I'm really describing its color. If I say something is, smells like strawberries, I'm describing its odor. So those are things we can talk about. Maybe its state. Is it a solid, liquid, a gas? But we can take it even a little bit further into things that now become a little bit more specific. What's its density? Density, remember, is a ratio of mass to volume. What's its melting point, boiling point? Those things are all physical properties because we can measure them and it doesn't change the identity of the substance. Now, the tricky one that people always think about is, well, melting point, right? If it melts, I go from, let's say ice to water, or if I boil it, I go from water to steam. Doesn't that change the identity of what we're dealing with? No, not really. Think about it. We have solid water, ice, liquid water, or gaseous water, steam. But we still have water in each one of these instances. So phase changes does not actually change the identity of something. Okay? Now, chemical properties, these describe the ability of a substance to react and form new substances. Okay. So what do you think might be an example of a chemical property?
The burning of wood.
Okay, why do you say that that's a chemical property, burning wood?
Because when you burn wood, first of all, you have wood. When you burn it, it turns into ashes. So you no longer have wood, you just have a pile of ashes. So it decomposes, it comes with combustion or whatever.
Yeah, that's exactly correct. When you go ahead and you combust something, you don't have the same material. Okay, so a very common example would be the combustion of methane gas. So this is a reaction, the combustion of methane on the left there with oxygen. We form carbon dioxide and water. Now, how do we know that this is a chemical property? Combustibility, flammability. reactivity. How do we know this is a chemical property? Because on the left, I have methane. And on the right, there's no methane anywhere. The carbon shows up here in carbon dioxide, and the hydrogen shows up here in water. So I produced two different substances. So measuring the flammability or combustibility of methane allows us, it is a chemical property, whereas I could take, I could take liquid water and I can boil it. This delta there, that little triangle means heat. And I can get out of this gaseous water. Yes, the phases have changed, right? Those have changed, but the identity of the substance is still water, and that remains the same. So we have a chemical, versus a physical.
Dr. Carlson?
Yeah.
I have a question. So technically, wouldn't all elements, would you say have chemical properties? Since technically, I mean, not all elements combine with all elements, but some do with others.
Yeah, I mean, I don't know of any substance except for maybe helium. But even that, I don't know of any substance that doesn't have some chemical property. One of the things that we'll end up talking about this semester are ions. Ions are, you know, elements that have gained or lost electrons. So ionizability, the ability to remove electrons. If I go from sodium metal to a sodium ion, those are two distinctly different substances. Therefore, the ease with which I can remove an electron to take sodium and form sodium ions, that is a chemical property. And there is, you can ionize anything. You put enough energy into it, you can ionize anything. Right? You can ionize you, Fausto. You can really milk anything with nipples. I have nipples, babe. Can you milk me? All right. So, we have chemical physical properties. Things also undergo changes, and that's really what we're focused a lot on here, is the different type of changes that substances can undergo. Changes. So in terms of changes, we also have physical and chemical. Keeping in mind our definition of physical and chemical properties, what do you think physical and chemical changes are? What do you think a physical change is?
The difference in color, like let's say you heat something and it'll change from one color to another.
No, that's actually a chemical change.
Like water, sorry, didn't mean to cut you off. Like water evaporating from liquid to,
Yeah. Okay. So that would be an example of it. A physical change is any change that still. So you can have a change in appearance without without a change in composition. So physical change, there is no change in composition. Okay. Whereas a chemical change, you have a new substance that's formed. So to give you an example, We can go like this. So this is tetrachlorocobalt 2. This is blue. However, when you heat it up, it turns red. This has undergone a color change, but the reason it's undergone a color change is because this substance that's attached to it, these anions, there's something called ligands, they have actually changed. And so we have changed the identity of the substance and hence the change in the color. Okay. Whew. So what I've written here, this is what's called a chemical equation. On the left-hand side, we have reactants. And on the right-hand side, we have products. We'll get into a lot more on there, but we also have phases. Oops, I forgot to write in the phase here. We have phases. The AQ means aqueous. This is a solution. We look at the formation of water. Like that. These are, that's hard to see. These are called coefficients. And we also have here subscripts. The coefficient applies to the substance, to everything in the substance that comes behind it. The subscript applies to only the species that comes immediately before it. All right, so keeping in mind our definition of physical and chemical changes, can you give me an example of a physical change?
A perfect example I would like to say is how rock candy is made. So it goes from like a liquid to a solid.
Okay, we'll buy that. We have aqueous sugar going to solid sugar, that's fine. Alexis, no, magnesium rusting, well, magnesium oxidizing, it doesn't rust, it oxidizes. That's not a physical change, it's actually chemical. America ice cube melting, yes, very good. Juan, you just have rubber, just one word. So I give you to ask, what's an example of a physical change? I get one word, rubber. Can you expand on that a little bit? Okay, so no, that's actually a chemical change. Yeah, it's actually a chemical change. Water freezing, yeah. Sawing a tree, yeah. Right. If you cut a tree down, and then you break it apart into logs, and then you break those logs apart, right? We're changing the shape, we're changing the size, but we still have wood. Good. Can someone give me an example of a chemical change now?
A firework.
Okay, fireworks, yeah, those going off. What else?
Would the burning of fuel be?
Yeah, absolutely. Yeah. Right, burning gasoline, burning diesel, burning any hydrocarbon for that matter.
Is baking a chemical change?
Baking is absolutely a chemical change. Copper becoming copper oxide from heat. Yeah, you heat a piece of copper and it turns black. Metal rusting, absolutely. Rusting of iron, rusting, yeah, yeah. Clay drying into a solid. So if you have clay and you dry it into a solid, what are you doing? You're actually removing the water. But you're not changing the clay. You still have the clay. It's just changing from a very, very thick viscous liquid to a solid. So clay drying into a solid, not quite. So what, yeah, boiling eggs, absolutely, right? Think about what you have to begin with, right? You've got a really, kind of liquidy, clear, transparent white in a runny, liquidy yellow yolk. And if you boil it, that yolk gets firm and crumbly, so it changes texture. The white becomes solid and opaque. You can't see through it. So yeah, that's good. Dana, making a cake, absolutely. Especially along the edges where the cake touches the cake pan, and you get that kind of crust that goes on there. Or when you bake bread, the crust of the bread, you actually have about 350 different chemical reactions that are occurring at that spot. So very good. So physical changes actually are not that easy to reverse. Think about cutting a tree down, or taking a log and breaking it apart and turning it into sawdust. Can you then go backwards and turn that back into a log? Yeah, I mean, it's debatable. I suppose you probably could make the argument that, oh yeah, you can. You just take it together and just glue it. Okay. So physical changes are sometimes hard to reverse, sometimes really, really easy to reverse. Same thing with chemical changes up. Okay.
Sorry,
Yeah.
Dr. Carlson. Going back to that, when you're saying, like, let's say reversing a physical change, where you cut down a tree and you want to put it back into log, if you do add glue, wouldn't that make it into a chemical change? Because now you're adding another reactant to it.
But see, let's say, so we'll say the sawdust, right, is just wood particles. Okay. If you add glue to hold them together, do you still have the wood particles? Have you changed the identity of the wood particles? No, you just stuck something that, you've just inserted something that makes them the wood particles stick together, but you still have the wood particles themselves. Whereas if you took that wood and you burned it, now you have ash and carbon dioxide. If I take that and I glue them together, I don't have wood particles. Now I've got ash and carbon dioxide particles that are stuck together. Does that make sense?
Yeah, that makes sense. Thank you.
Yeah. And some chemical changes are actually quite reversible. So this reaction right here, right, if I just take the heat away, I can actually cause it to go the other direction. So it's fair to say that physical changes can be reversed sometimes, but so can chemical. So we don't want to get in the habit of making those general statements there. Okay. Other questions?
What about like butterfly tea, where you put a lime in it and it changes from blue to purple?
Butterfly
tea.
Butterfly pea?
Butterfly
Like litmus
tea.
paper.
Butterfly tea. This is interesting. Hold on, let me see. P like urine? Or P like
No,
PEA?
it's like an actual tea and it's called butterfly PT.
P as in like
P.
the
Like
peas in
peas.
your din. Yeah, like peas.
Did you see that on, did you see that on TikTok?
Wouldn't that be a chemical change since it changes the pH?
Yeah,
Cause
so this
it goes
is,
from acidic to like a alkaline.
yeah, so this is what we're talking about here. Give me just a moment.
PEA.
Yeah, yeah. So we can see here, right? We've got two different glasses of this butterfly pea tea, and we can see that they're squeezing a lime into this one, and it's going from this purple color to this blue color. And
Actually, the opposite.
it goes from the blue to the purple.
Yes.
Yes.
Okay. Well, Angel hit it right on the head. Right. What we are doing here is we're adding acid. And so the butterfly tea, most teas themselves actually tend to be slightly basic. And adding the lime juice, the citric acid, ascorbic acid, and other things in the lime juice, they react with the base that's present in the tea. So this actually functions as an acid base indicator. This is something that we'll get into in Chem 229, so second semester Gen Chem. But yeah, this is a chemical change, because, and I'll show you kind of why it's a chemical change. Okay, so let's say we have butterfly PT. Okay, what we're adding when we add, let's say this is lime juice. That's not how you spell lime juice. When we're adding lime juice, we're really adding hydrogen ions, amongst other things, but the hydrogen ions are the ones that are reacting. And what we get out of this is a protonated form of this thing. So this is aqueous, this is aqueous, this is aqueous. Now, you can ask yourself, well, is this really all that different? And I look and I see I've got I've got BPT here, and I've got HBPT plus. And so the fact that those two, oh, hold on. Okay, I have BPT here and HBPT plus. And the fact that those two things are different should tell us, hey, this is a chemical reaction. That's really neat. I'll have to get some of that tea. Is it good? Have you had it?
Yes, I actually have some.
What does it taste like?
Nothing.
Tastes like nothing?
Yeah, it's not that much flavor to it. It's just the lime that gives it the extra flavor.
It tastes like a butterfly? America, you go around eating butterflies? You weirdo.
If you ever see her nervous, just don't question it. She has butterflies in her stomach. That's it.
Oh.
Thanks.
Oh, and I forgot to update my calendar here. Let's see. I got some jokes for you. So there's a person on crutches who stole a camouflage jacket of mine. He can run, but he can't hide. Wait, he can run. Never mind, I screwed that one up. Never mind, forget it. Why aren't dogs good dancers? They have 2 left feet. Wow. Ava had to unmute herself to give me that pity laugh.
I'm gonna ask me why.
Dr. Carlson, that was it there.
Yeah. I tell a lot of knock jokes, but I just adore them. Adore them. What do you call a dog that does magic tricks?
What?
What?
A labracadabrador.
Like,
That one was funny. That one was funny.
That was good.
Did you hear about the boy who went to mime school? He was never heard
No.
from again.
That was smart.
Where did you get these from, Professor?
My
I'm pretty
calendar.
sure you got from Google.
Oh, no. It's my calendar.
Oh, wow. It's cool.
Why is
Yeah.
that iron a 4-leaf?
Oh, that was jokes. That's awesome.
I met a taxidermist who wasn't very talkative. I asked him what he did for a living. He just said stuff.
Wow, that's super dry.
Professor,
Yeah.
why is it? Why shouldn't you iron a 4-leaf clover?
I don't know why.
Because you shouldn't press your luck.
Oh, okay. I'll get you guys got back up on Wednesday. What type of magazines do cows read? Catalogs. What's a mermaid's favorite laundry detergent? Tide.
Professor, I like how you're saying these jokes with like a one tone, like no type of any.
Tide. Yeah.
Right.
Dad jokes 101.
Oh, seriously.
He's a master at these jokes.
Okay.
Good.
Back to what we were talking about. Well, we finished that. So we're going to jump into a new topic. We're going to talk about energy. Okay. So energy is just something's ability to do work. So when we talk about energy, we actually have two different types of energy. We have potential energy. And we have kinetic energy. What's the difference between these two?
One has
Potential is-
potential to create energy, whereas the other one already has energy.
Kind of. What were you going to say, Justin?
Potential energy is like what it can do, and then kinetic energy is what it gives off.
Okay. Anyone else?
Potential is stored, kinetic
Yeah.
is, I don't know, acted.
Yeah, so potential energy is stored energy. Kinetic energy is energy due to motion. Okay. So potential is based on location. Stored energy, we can talk about things like, we can talk about mechanical stored energy. So hydroelectric dams, the Hoover Dam, these are stored mechanical energy based on its position. So the dam works by, stopping water and allowing it to build up behind the dam, and then allowing the water to flow down through pipes. And as it flows down, it spins a turbine and it releases its stored potential energy as motion spinning these turbines. We
Can you
could have,
also-
go ahead.
Sorry. Can you also consider solar energy as potential energy?
Solar energy? You're asking about solar?
Yes.
Kind of. So what happens in a, do you know what happens in a solar cell? Okay, so a solar cell works is something called a semiconductor. This is way beyond our class, but It's kind of neat. There are, you can imagine in the atomic layer, there are little holes, and there are two different types of holes, p-type and n-type holes. And what happens is that when photons, which are basically particles of light, strike a solar cell, they take an electron from an n-type hole and they bump it to a p-type hole. And then that electron can then fall down, and when it falls down from the p-type hole to the n-type hole, it releases that energy. So in the sense, so the electrons that are in the higher hole, those have stored energy. So those have a potential. And when they fall, they release that energy, creating kinetic energy, which then is usually harnessed and stored in a battery. So yeah, there's probably some potential energy. There's probably some kinetic energy in there as well. For our purposes, in terms of chemistry, we're going to find potential energy in the chemical bonds. Okay, so this is stored energy. This is potential energy is chemical bonds. When we break a chemical bond, we release. When we break a chemical bond, it requires energy, and when we release, when we form a chemical bond, we release that energy. So if you think about, if you burn some gasoline, that's going to get hot, it's going to release heat. What that tells us then is we're breaking the chemical bonds in the reactants, and we're forming the chemical bonds in the products. And because it's releasing heat, there must be more energy released from the bonds in the products than the reactants. Okay. Kinetic energy, it might be the pressure exerted by a gas, it might be the energy released when two moving objects collide, it's the energy that's due to motion there. Go ahead.
So does that mean that kinetic energy is just an effect of the potential energy?
No, it's a different type of energy. So we can calculate potential energy based on something's position, whereas the kinetic energy that we can calculate is based on something's mass and velocity.
So for example, a rolling ball would be kinetic energy?
A rolling ball has kinetic energy, and based on where its location is, it also has a certain amount of potential energy. All right, let's take a look. If we have, let's say, a hill up here, and we have a ball here, okay, at position 1, it has a certain potential energy. Okay, let's say then it moves down, and now it's right here at position 2. Here it has, because it's moving, there's some moving for you. Because it's moving, it has kinetic energy, but it also has a certain potential energy, again, based upon its position. And then finally, let's say it makes it down here and then stops at position 3. Now it only has potential energy again. Okay, so as long as the ball's moving, it's got kinetic energy and potential energy based on its location. When it stops, it has only potential energy. So the difference between the potential energy at stop 1 and the potential energy at stop 3, that must be the amount of kinetic energy it lost. So go ahead.
So what if it goes, what if it's like reverse, if it goes uphill?
If it goes uphill, so then it's going to, as long as it's moving, right, it's going to be gaining potential energy. So it won't spontaneously on its own roll uphill. You would have to put energy into it. But if you took the ball, you took it here, picked it up and put it uphill, now you're giving it potential energy. Okay, you're transferring your energy, your kinetic energy, and moving the ball up the hill. You're transferring that kinetic energy into potential energy for the ball, which allows us to say that there's something in the law called the law of conservation of energy. Okay. This says that the energy of the universe is constant. So another way of saying that is energy can be converted from one form to another, but not destroyed.
Professor,
Yeah, go ahead.
from the last example you had, would like the mass of an object affect the kinetic and potential energy?
It wouldn't affect its potential energy, but it would absolutely affect its kinetic energy. Yeah, and so this is why, you know, which would you rather be hit in the face with? You know, a stuffed teddy bear flying at 15 miles an hour, or a brick flying at 15 miles an hour?
A teddy
I'll
bear?
take the bear.
Yeah, probably the teddy bear, right? And that's because now what's going to happen, right? That whatever object is moving, so it has a certain amount of kinetic energy. When it collides with your face, it stops moving. That energy has to be transferred somewhere, and so it gets transferred into your face, and then your face starts moving. You also there's a few other things that go on there, right? There's you know, if it's the brick, it's probably going to break some bones, right? Breaking those bones, that's going to require energy. So, you know, it absolutely depends on the mass of the object.
Wait, so does everything have like a certain amount of potential energy, even if it's standing still or like not moving?
Yeah, absolutely. Right?
Yeah, hey, Dr.
It's
Carlson,
based
sorry.
on position. Okay, so if I hold this pencil or pen or whatever you want to call it here, it has a certain amount of potential energy. If I hold it here and I don't move it, it now has more potential energy. That's mass times the acceleration due to gravity. So, what's up, Fausto?
Yeah, on that point, is it possible that an object or anything in that matter has potential energy but not kinetic energy, or vice versa?
Yeah, absolutely. I'm disinclined to say that it doesn't have any potential energy. Right? It can have kinetic energy and potential energy. I'm disinclined to say that it's going to have, at some point, it's not going to have any potential energy. Anything else?
And that would count even like in an object in like the vacuum of space, there's still potential energy.
Probably. Well, yes. Right? Why do satellites, you know, eventually, why would they crash into Earth? Well, they're attracted due to gravity. And the potential energy that an object has is going to depend on its distance away from the Earth, and so it's going to have a certain, you know, it can, it's going to feel the attraction due to gravity, and that's going to determine its potential energy. Excuse me. Okay. Let's see. So energy, for the most part, energy changes are not terribly efficient. Can anyone guess the efficiency of a regular gasoline engine for a car?
Like 30%.
Yeah, it's about 30%. Really good processes, reactions, or physical chemical changes, right? Really good ones have efficiencies 80, 90, 95%. Nothing is 100% efficient. There's always a loss of energy somewhere. But the internal combustion engine is notoriously inefficient.
Because isn't most of it the energy heat that goes through the exhaust?
That's exactly correct. Most of it's converted into heat. This is why, you know, so if we could get the internal combustion engine more efficient, we would take, let's say, gas mileage, like an average gas mileage of maybe 25 miles to gallon. We could take it up to 80 or 90 miles to gallon because it would be much more efficient. This is why if you look at electric cars, they don't report an average MPG because they can't. They don't have gallons of gasoline, but they report MPGe, which is basically an electric equivalent of miles per gallon. And you would find for electric vehicles that their equivalent mileage is between 40 to 60 miles per gallon. Why is it so much higher? Well, it has to do with the fact that for an internal combustion engine, what do we have to do? We have to take the gasoline, we have to take it from a liquid, we have to basically vaporize it into a gas, and then we have to combust it. And that combustion does two things. It releases a lot of heat, and then it takes the gas and expands it and drives a piston. Okay? And then those pistons, you know, drive a drive shaft, and those drive shafts go through a differential and turn your wheels. How does an electric car work? There's an electric motor at the wheel. It turns on. That's it. So the fact that there are so many fewer steps that the power source for an electric car has means it's going to be, by definition, be more efficient. Every single step that you go through, you lose a little bit of energy. There's an energy tax, if you will. Now, if everything were perfect, you know, we could put, you know, 100 kilojoules of energy into a system and get out 100 kilojoules of energy later, and then put it back in and get it out, put it back in and get it out. What usually happens is we put 100 in and we get 85 out. And if we put that 85 back in, we get 60 something out. And so every single time we lose a little bit of energy. All right, the last thing we're going to talk about is how we actually measure energy. So the SI system, this is the system of units that scientists use, that we as chemists are going to use. We use things like, we measure distance in meters, we measure time in seconds, we measure volume in meters cubed or milliliters or liters, we measure temperature in Celsius, we measure energy in joules. In joules. 1 joule is equal to 1 kilogram meter squared per second squared. So one, do you have a question, Abigail? So 1 joule is the amount of energy required to move a mass of 1 kilogram through a distance of 1 meter at a speed of a meter per second squared. Sorry, an acceleration of a meter per second squared. Now, that's what we use, and we'll end up using that later on, but there's another form of energy, another measure of energy, and that is the calorie. Notice I've written it with a lowercase c. There are 2 types of calories, but 1 calorie is equal to 4.184 joules. There's also 1 big C calorie, which is equal to 1,000 little c calories. This is what's called a nutritional calorie. So a nutritional calorie, these are the ones that we see on bottles or on food. We might also call them or a 1 kcal, where this K is the scientific prefix meaning kilo or 1,000. There's also a kilojoule, which is 1,000 joules. So we use kilojoules and kilocalories because joules and calories themselves are actually quite small. So for our purposes, we're going to focus on just the joule, kilojoule. What can you tell me about the difference between heat and temperature?
Would heat be like the actual like movement of the molecules, and temperature is like the effects of that?
So temperature, yeah, you're kind of right. Temperature is a measure of the heat. Heat is how much thermal energy something has or will transfer. Temperature is a measurement of that. And so the easiest way to think about it is, you know, if you have a cup of water in a small saucepan versus a gallon of water, and you want to take both of them up to boiling, which one's going to boil faster? Let's say you heat them both up. You turn on the burners, you heat them both up. Which one's going to boil faster?
The one that has the more measured heat.
So the one that heat is the amount of thermal energy something has. So the cup of water is going to boil faster. And the reason it's going to boil faster is because there's less of it. Therefore, it takes less heat to increase its temperature. So we are going to